Got it? Is it bouncing? La 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 la. All right, I'll begin with the word of prayer. Dear Father, we thank you for this day. Just help me to keep the coughing to a minimum and help us to understand a little bit more about Calculus 2 together today, Lord. In your name I pray. Amen. I think I need to post more solutions for you guys. I keep forgetting to. If you asked me, I would. So if I forget, it would be good for you to send me an email saying, hey, we want solutions. Okay. And have I put problems on second order differential equations in the homework list? Like y prime prime plus 3y prime plus 2y equals 0, stuff like that? I meant to remove those. If they're still there, that's an error. Right? If you find differential equations that we haven't said a lick about in your homework list, that's an error. I think I fixed that already, though. Okay, good. It's kind of a it's a haze for me. I don't remember what has occurred. Okay, so the limit we defined carefully last time. I want to show you. There's some important properties of this. Everybody should see this at least once.
Dr. Cook?
Yep.
Real quick, Corey, sorry, but I have a question about homework. Is that for later?
Well, what about it?
Just 16.
Which section?
Oh, 11.1. I'm not sure how to go about finding the GLB and
Yeah, by the way, I don't mind you guys interrupting and asking homework questions. I just forget to ask sometimes. It's not usually on purpose. So I do appreciate you interrupting. It is welcomed, in fact, applauded. Number 16. So here we're supposed to find the least upper bound and greatest lower bound if it exists. So basically what he's asking you to do is to wrap your mind around what on earth this set is, right? Once you understand what it is, those questions are easy to answer. So we're supposed to find, okay, so what I would do is I would say that that's x minus 1/2 quantity squared, right? Plus what? Completing the square there. Yeah, 7/4, yeah, I think that's right. So the question, for what x is this greater than or equal to 0? Graphically, he's asking you the question. You have a quadratic function. Its graph has a vertex at 1/2 and looks to me like 7/4, right? And its y-intercept is 2. It's basically graphically what you're looking at is something like this. And it's asking you for which x are the outputs positive, not negative, rather.
Solve, right? So any greater than. Can't you just solve that?
Why would you solve for x? You're looking for x such that the quantity x squared plus x plus 2 is greater than or equal to 0. Yes, it's all x.
All x, yeah.
Yeah, this is just the reals. So there is no least upper bound or greatest lower bound. Greatest. I mean, there's just. Is it a trick question? I don't know. A more exciting one would be if I put a minus here. Right? Then instead of having plus 7/4, I would have, minus 3/2, right? Or 6/4 if you prefer. Is that right? No, you're not. I can't do math.
Wouldn't it? That'd be plus on the other side of this. 1 square.
I'm changing the problem. Suppose that was a minus, then what would happen? minus 9/4, yeah, that's what I was looking for. So if that was the case, then this factors x minus 1/2 minus 3/2, x minus 1/2 plus 3/2 greater than or equal to 0 is the question. I draw a number line. I put my critical numbers. What happened?
In parentheses, it's supposed to be plus, right? Because otherwise the top one would be minus x. So it's supposed to be in parentheses x plus 1.
Oh, right. Thank you. Very good point. Yeah, I'm an idiot. Going back to the original problem, that should have been a plus, but it doesn't change anything either. Like my analysis doesn't change, but that was a wrong step. Thank you. That does matter here, though. Thank you. So if I have that, then that makes this a plus and a plus, right? So that makes this minus 1/2 plus 3/2 for the 1 point, and over here, minus 1/2 minus 3/2, also known as 1, yeah, and
2.
-2, yeah. So this is a very, very wrong way to draw a number line. Now I can fix it, but don't do that. Of course, if I had half a brain, or at least a functioning one, I would have done what? D George, plus 2, x minus 1, right? Yeah. So completing the square is kind of like killing a mosquito with a sledgehammer here. There's really no need for it. And have you ever tried to kill a mosquito with a sledgehammer? It's really difficult. Let's see here. See here. So I really should draw it that way. And then let's sign chart technique. This is a parabola which opens up. So it's got pluses over here, pluses over here. It's minus where it dips between the x-intercepts. And so the solution set to my modified problem would be like minus infinity to minus 2 unioned with 1 to infinity. This again has no greatest lower bound or least upper bound because it goes on and on both ways, right? You might be tempted to say that minus 2 is like the greatest upper bound, and 1 is the least, what did I say, least upper bound, and this is the greatest lower bound, but that's just wrong. You can't do that. I'm sorry. Do you guys have other questions? Let me stop making up questions we don't need to answer. But all of these in 11.1 are basically this kind of, you just have to think about it for a while, come to understanding what the set is. That's the point of these problems, actually. To analyze it, to think, yes. All right. Let me move along here. I'm supposed to be doing L'Hopital's rule today, so let me get to it,
Why is no greatest lower bound on a parabola? Isn't it the lowest point?
Well, it's not y. It's not y such that y is equal to this. It's x.
Yeah.
So it's asking about basically what's the domain, what are the inputs to the parabola such that this parabola is positive? Well, this is a everywhere positive parabola, so Sorry. Let's try to keep Bill Cosby out of this. Let's see here. Where are we? Yes, what I was going to tell you, and this is an utterly unsurprising thing, is that limits are unique. So suppose you had the limit of f of x is equal, n is equal to L1. Let me say a sub n is L1, right? And suppose you also had that the limit of a sub n was equal to L2, right? Then, too far. If you look at I'm not going to prove this, but you guys, what's the limit of 0? I mean, I could prove it, but let me not. Let me just not do that this semester. This is 0, all right? The limit of a constant is 0. Just like functions, the sequences work much the same. And this, on the other hand, is the limit as n goes to infinity of a sub n minus a sub n, right? But that would be the limit as n goes to infinity of a sub n minus the limit as n goes to infinity of a sub n. So if this one is L1 and this one is L2, what do you get? Yeah, you get L1 minus L2. In other words, 0 is equal to L1 minus L2. Therefore, L1 is equal to L2. So the limit for us, if it exists, is unique. This is a straightforward consequence of linearity of the limit. All right? That's really not that surprising, is it? Okay. But it's important. So if you're tempted to say things like the limit is both 1 and minus 1, you can't do it. All right? Like this. No, this is not L'Hopital's rule. No. It's not a rule at all. This is just an observation. All right. We talked about bounded sequences. I should have mentioned to you every unbounded sequence is divergent. Why is that true? How would we know that every unbounded sequence is divergent? What did we prove last time? At the end of class, what did we show? We showed that a convergent sequence is what? We proved that they're bounded, right? So, what would it mean that if you had an unbounded sequence which was convergent, that would violate what we proved last time, right? Because we proved that if it is convergent, it's bounded. So if you had an unbounded one which was also convergent, that would not be consistent with this, would it? Oh. All right, so there's that. I showed you the limit laws last time. I'm not going to prove those for you since you didn't want me to. And then theorem 11.3.9, important, is that if we have a sub n less than or equal to b sub n less than or equal to c sub n, all right, for n sufficiently large, let me say for n much, much bigger than 1. So if you go on out far enough, if eventually these inequalities are preserved, all right, then, and if a sub n goes to L and c sub n goes to L, then punchline, b sub n also goes to L. What's interesting about this theorem is that here we do what? We assume the existence of the a sub n and c sub n limits, right? But we get existence of the middle limit. So in order to use this so-called squeeze theorem, right? Sometimes called also known as what? The sandwich theorem, et cetera, et cetera, et cetera. The beautiful thing about the squeeze theorem is it gives us the existence of this middle sequence without actually without having to compute anything about it directly. Basically, through peer pressure, we force the limit of the B sub n to be L. Let me show you a standard example. So I could have, let's say, B sub n equals to 1 over n, n times the sine of 1 over n. It's a pretty standard example. Suppose you want to calculate the limit of that as n goes to infinity. Right? What's the trouble with that? Oh, this isn't a good one. I think just a second here. Let me adjust this. Sorry, I gotta think a little bit more here. It's 1 over n times n is what I'm looking for, I believe. Yeah. So what's the limit as n? I mean, why can't I use the limit laws from last time? So like limit, what's the trouble with this? Limit as n goes to infinity of 1 over n times the sine of n. Why can't I just calculate that? Right? Why don't I just say, okay, so it's the limit as n goes to infinity of 1 over n, right? Limit as n goes to infinity of sine of n. Why can't I just do that? In order to use the limit laws, right, we have to presuppose that the limits that we're coming to exist, right? But the limit as n goes to infinity of sine n does not exist because sine oscillates, right? It doesn't settle on 1 or minus 1 or any. I mean, this does not exist. So this does not exist. And this is an illegitimate use of the product rule for limits. All right? You can't do that. In practice, you do that, all right? But then once you've done it, you say, oh, wait a minute. Hold on a second. I got to go back and say, oh, I couldn't do that. And then you try something else. So in this case, we'll try the squeeze theorem. What do you know about sine? Really one thing. Minus 1 less than sine n less than 1. Sine is stuck between plus or minus 1, right? And then you can take this inequality if n is greater than or equal to 1. And after all, that is what we're interested in, isn't it? For a sequence. So I can divide this by n. And that gives me minus 1 over n less than 1 over n. Sine of n is less than 1 over n. And so identify, we have a sub n equals to 1 over minus 1 over n, and c sub n equals to 1 over n. These both go to 0, right? Therefore, by squeeze, 1 over n times the sine of n also goes to 0. So even though I cannot calculate the limit of sine of n directly, it doesn't matter. Squeeze theorem says this limit exists, and ultimately the 1 over n wins and forces this thing to 0. Does that make sense? Well, I don't know. I guess I don't much care if it makes sense or not. Here's the legitimate use of the squeeze theorem. I do care. It's not true. I do care, actually. It's true. I care. Let's see here. Something that's worth pointing out at this juncture. He says if you have that the absolute value of b sub n, right, is less than or equal to Cn for n sufficiently large, which I like to write as n much, much bigger than 1, all right? That's just my way of saying it's big. Well, if C sub n goes to 0, then what? Then B sub n goes to 0. He says this is basically a corollary to the squeeze theorem. Can you guys see why this is true? Maybe you can see intuitively why it's true. Can you see why the squeeze theorem gives this to you? what's this mean? The absolute value of b sub n, right, is less than or equal to Cn. What's that? Unpack that in terms of inequalities. What's this mean? If I have the absolute value of x is less than epsilon, that tells me that minus epsilon is less than x is less than epsilon. That's the way it works. So like this tells me minus Cn, I was about to write b, I'm an idiot, less than Bn, less than Cn. Right? In fact, it's not just, it's both ways. These are interchangeable. And, oh, yeah, that's true. Thank you. And so, squeeze. So this goes to 0. This goes to 0. Consequently, by squeeze theorem, that goes to 0. Make sense? All right. That's often, this is a useful one sometimes.
Always assume that,
Sorry, what?
can you always assume that if Cn goes to 0, that negative Cn goes to 0?
Yeah, yeah. That's from the limit law we stated last time. Limit of c times the limit is c times the limit. C times the function. This guy. What's that? You want me to prove it?
Yeah.
No, I'm just kidding. All right. Now, section 11.4 is full of deep truths. And last time I taught this course, I spent the better part of, I don't know, 3 or 4 class days working out section 11.4. My reward for this hard work was epically low student evaluations, so I'm not doing it again. If you'd like to see section 11.4 proved, you can look at the videos. They're all there. I go through it blow by glorious blow, bit by bit, piece by piece last year. Watch the later section. It's the better one. I will tell you these. What's that? Oh. One of last year's participants is agreeing with my decision to omit the proofs here. Section 11.4. But nevertheless, proofs omitted or not, these are things that we must know to use.
What's your squiggly S?
Section 1. And this is all n going to infinity. Let me just rattle these off for you. X to the 1 over n goes to 1 for all x greater than 0. Item 2, x to the n goes to 0 if the absolute value of x is less than 1. Some of these are real snooze fests. 1 over n to the alpha, I mean, how could this not be true, right? Like this, look at this. I'm saying that if you have a number with magnitude less than 1 and you raise it to the infinity power, it goes to 0. Of course that's true, right? If you take like a half times 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 a half, it gets really, really small, right? And the same with minus a half. So as long as the absolute value of the number is between plus or minus 1, you can prove that. 1 over n to the alpha goes to 0 for any alpha greater than 0. So if you have a positive reciprocal power, it goes to 0. For one of these I should actually prove because it involves important techniques for this course. Maybe it's this one. X to the n over n factorial. We talked about Mr. n factorial last time, although I don't think I introduced him properly. This goes to 0 for all real x. 5. Some of these I'm going to prove from L'Hopital's rule if you don't mind. The log of n, like this one, log of n over n goes to 0. This one's a little bit more weird. N to the 1 over n power, well, that was interesting, goes to 1. And then 7, 1 plus x over n to the n goes to e to the x. So 11.4 carefully proves these assertions, bit by glorious bit, each result leading to the next, all right? So, but I think a lot of these, we probably can reproduce from L'Hopital's rule, so I'm going to show you how to do that. Well, I'll know it when I see it. So let's talk about L'Hopital's rule. All right, so first of all, let me just say what we don't need L'Hopital's rule for. All of these like sort of obvious limits, right? So let me show you some obvious limits. When no need. Basically, if your a sub n has formula, right? Which is determinate. As n goes to infinity. Let me show you some examples of that. If you don't mind, I'm using common sense rather than proof this semester. Hope that's okay with you. N squared plus 7. What happens to n squared plus 7 as n goes to infinity? Goes to what? Infinity, all right. What happens if we have a sub n is equal to 1 over n squared plus 7? Goes to 0, very good. A sub n equals to, I don't know, sine of n. We just talked about this a second ago. Does not exist because there's no hope for it. That's actually not determinate, it's hopelessly indeterminate, all right? I mean, it's oscillatory, whatever you want to call it. A sub n equals the square root of n plus e to the n, all right? This goes to infinity because the exponential and n both get super large, and the square root of something super large is still super big, all right? A sub n equals to the inverse tangent of n squared plus 43. It doesn't really matter what you feed the inverse tangent. If the input to the inverse tangent gets really, really large, by our vast knowledge of trigonometry and precalculus, we know that this goes to pi over 2, right? All of these things, in fact, basically any rational function, right? Any rational function, let's say p of n over q of n, where the degree of q is strictly greater than the degree of p. Guess what? Game over. This goes to 0. This you can prove by just dividing by the largest power of n on the numerator. Right? Here, you don't believe me about this one? So like Pn would be something like a naught plus a1n plus plus ak n to the k. And downstairs you'd have something like b naught plus b1n plus plus, what is it?
Can you move your left hand? I can't see.
B sub j, n to the j. And I'm assuming that j is strictly greater than k.
What are the degrees? Should we know what that means?
Should you know what the degree of a polynomial means?
Oh.
Power.
See, once I said it that way, you knew it. Yeah. It's just my scribbling. It made sense. So up here, so like here, I'm going to unravel this, why this is true. The degree of my numerator is k. The degree of my denominator is j. I'm going to assume j is strictly larger than k, okay? Pun intended. And so if I divide by, what did I say? I think I need to divide by n to the k, right? So I've got like a naught over n to the k plus a1 over n to the k minus 1 plus da-da-da-da plus what? Plus a sub k, all divided by what? B naught over n to the k plus, goodness gracious, k minus 1, b sub j, did I choose poorly? N to the j minus k? What did I do? Yeah, minus k. What do I mean n sub n? That doesn't make sense. Oh, n to the k, thank you. Something happened in my head. So, yeah, up here there's an a k minus 1 n, and then finally a to the k is constant in my, what is that? So what happens to all of these things? Let me see, I'm not sure. So this is 0, right? 0, 0, 0, 0, 0. What? I'm an idiot. You're saying that's division by n? Thank you. That's 0. This is just a sub k, right? So this is like, essentially, this is basically going to a sub k over what? This is, what, j minus k is what? Is this a negative or positive power?
Is that?
I agree with you. All right, so we've got b times n, b sub, basically b sub j to the j minus k, right?
Is that a? I'm like, I'm sorry, I'm still trying to write this down. Is it a naught over, what is that, nk, or is that ak?
N to the k.
Oh.
Sorry, my bad. Anyway, my point is, after you make this simplification, it becomes clear you've just got something non-zero divided by some number times n to a positive power. What happens to this as n goes to infinity? So this goes to a very large positive, I mean, this goes to something very large. When you divide by something very large, this whole thing goes to 0, right? This is not indeterminate, it's just complicated. None of these things I need L'Hopital's rule for, right? Although I could use L'Hopital's rule on this one. Let me show you what L'Hopital's rule says. If a sub n and b sub n go to 0, right? Or a sub n and b sub n go to infinity. Could be plus or minus infinity, doesn't really matter. I'm not talking about the sign here. Then the limit of the quotient, a sub n over b sub n, is equal to the limit as n goes to infinity of the derivative of a sub n divided by the derivative of b sub n. Now, you should say, cheater, cheater, you can't differentiate here, right? Why can't I differentiate here? It's not a real variable, right? Can you differentiate with respect to a discrete variable? Technically, no, right? You need a continuum of values of x in order to take infinitesimal changes in x to calculate the derivative as a quotient, like we talk about in Calculus 1, right? So, but there's a corresponding L'Hopital's rule for functions, all right? So like L'Hopital's rule for functions is this, you know, limit as x goes to infinity. There's various forms of L'Hopital's rule. This is the one we're interested in. So if you have like this is equal to this. And that would make sense if f and x are differentiable functions and we have the limit of f equals to the limit of g is either 0 or infinity. This is the This is the function version of L'Hopital's rule, all right? We want to talk about both. So technically speaking, my L'Hopital's rule is so offensive to mathematicians, we insist you write something off to the side, right? We put in parentheses, extending n continuously, which is fancy speak for you take the sequence, you replace it with the function which agrees with the sequence at the whole numbers, you differentiate that function, you obtain the result, and then you translate back to sequences. But since this is all trivial, these steps I just mentioned, and it's mostly mathematicians who care about them, you guys are mostly not mathematicians, let us just agree that we will content ourselves to write extending n continuously in the margin, and we'll be happy about our life as we apply L'Hopital's rule.
You want us to do that every time?
Yeah.
Wait, you want us to do what? Extending it.
Yes, that's a penance we must pay for not spending a half hour of class time on that theorem, if that's okay with you guys. Is that an acceptable form of penance? Okay, that's good. That's good. Example. Example, limit as n goes to infinity. Let me start out with something like that. Well, not quite like that. N squared plus 2n plus 1. Now, I don't really need L'Hopital's rule for this, do I? First of all, I can't just, I don't know what happens here at infinity. Okay, that's not true. I know what it is. It's 1. I know that the answer is 1 because the leading coefficients of the top and the bottom are 1, and they match. So the answer is that. I know that. It's true. I'll admit it. But by L'Hopital's rule, here's how we do it. So the top and the bottom are both going to infinity. So here's my notation. Funny looking L, infinity over infinity. This tells me I'm using L'Hopital's rule, right? So I got 2n plus 2 divided by 2n plus 3. You're like, don't you have to do the don't you have to do the quotient rule? All right, I feel better. I've now done my due diligence. I'll tell you what, if we write this once, we're good. Does that sound good? All right, so it's already been extended continuously. Now you do it again. See, because this is still infinity over infinity. Two over 2. At this point, we no longer have an indeterminate limit. We have a determinate limit, right? 2 over 2 is just 1. What's the limit of 1 as 1 goes to infinity? As n goes to 1 goes to infinity. Listen to me. So the answer is un. Now, do I need L'Hopital's rule for this? Not really. I could use limit laws on this one, couldn't I? The limit law solution would look something like this. So just divide the top and the bottom by n squared, 1 plus 2 over n plus 1 over n squared divided by 1 plus 3 over n. I was hoping to communicate this notion with this, but it's too complicated what I chose as an example to illustrate. My bad. So, I mean, is algebra an easier path here? Algebra is less writing here, honestly. So all of these go to 0, right? So this is just equal to the limit as n goes to infinity, 1 over 1, which is 1. So I think the algebra path is an easier one here. To be completely honest with you guys, if I put this on a test, I really just want you to be able to tell me the answer with confidence. I don't really grade work on this kind of problem, honestly. I'm just happy if people can find the right answer at this point in my life. I have smaller goals. Can we prove any of these? How many of you guys saw L'Hopital's rule for like functions in Calc 1? A lot of you. So this is really the same song and dance, right? But others of you have not seen it, so bear with me. I have to try to hit all of the important examples. What if we have the limit as n goes to infinity of like n e to the minus n. Excuse me. This is type. So let me tell you some ways you can lose points here. All right, so you guys are always like, I have too many points. I would like to lose some points. Please tell me how to lose points. I'm so glad you asked. A very simple thing you can do. Equality. Forget about it. Don't bother with equality. These equals I'm writing here, these L's I'm writing, doesn't matter. Just forget about it. Just scribble this and make an arrow to that, to that, to that, and like, don't tell me what you're doing. I'll take all your points. Not entirely true. There's a way to write this without limits. But, you know, I write limits not just to see myself write limits. It's because it's expressing a very precise mathematical idea. I want you to write those. Or there's another way, which I will not show you. Just to be mean. All right, so what's that? You hate writing limit? Oh. Maybe limits hate writing you. No, that doesn't make sense. That doesn't even make sense. I'm sorry. But this is type infinity times 0, right? So if you see something type infinity times 0, that does not mean it's 0, and it does not mean it's infinity. It means it could be anything. This is an indeterminate form. You have to do work to determine what it actually works out to. L'Hopital's rule gives you a tool to do that. Pretty efficiently, what you do is just rewrite it as a fraction, right? So I rewrite this 0 as like 1 over infinity, basically, right? That's the idea. And now I can apply L'Hopital's rule to that. It's type infinity over infinity. N goes to infinity. 1 e to the n. And okay, fine, extending n continuously. I think I found a, oh look, that's better, isn't it? Okay, we'll work on that abbreviation. And then, so that's, well, it's no longer, there you go, 0. 0, 1 this time. It happens to be 0 in this case. ENC. I don't know. Don't ask me yet. Let me write it about 15 more times before I commit to that. Limit as n goes to infinity of the natural log of n over n. See, this was proved using careful jibber jabber back in section 11.4. We will now dispatch it with ease with the hammer that is known as L'Hopital's rule. So this has type infinity over infinity because log goes to infinity and n goes to, well, of course n goes to infinity as n goes to infinity. That seems kind of inescapable. So here you go, extending n to be continuous, we apply L'Hopital's rule. Fine. I'm already starting to regret that. Anyway, so this, the derivative of the top is 1 over n. The derivative of the bottom is just 1. So just one more step to clean things up. 1 over n, limit of 1 over n as n goes to infinity is 0. By what? By this semester, by common sense. 1 over n is 1 over a very large number. As n goes to infinity, that goes to 0, right? That's, you could prove it. I did prove it last year, semester, whenever it was. I taught this course before. I forget. It was last semester. Yeah. So there it is. Now this one's a little bit more mysterious, isn't it? Let's see if we can get those. Yeah. I'm sorry?
Like, you know, like pretty looking out.
Yeah.
So
Yeah.
we need to put that
You either have to write it through the equal sign, or you have to write over here, I'm using L'Hopital's rule. Somewhere you must explain to me what you're doing, yes.
So, what if we just use it once? That's cool.
If you just use it once, but if you use it twice, then you should write two L's. Oh, erased it. You know, it depends on, yeah. Let's see here. How about, well, okay, I guess in you know, just truth in advertising here. 6 and 7, I'll get to next time. I don't want to try to squeeze them into the first day. Tomorrow we'll talk about how to deal with powers, indeterminate powers. What are the indeterminate powers? You got yourself 0 to the 0, you got yourself 1 to the infinity, you got yourself infinity to the 0. Any of these patterns, if you have limits that are going, you know, you have two things, f to the power g. If f is going to 0 and g is going to either 0, you know, if you have these patterns, these are indeterminate powers. You have to apply L'Hopital's rule and some careful argumentation to figure out how those go. All right? Let me do another example here. Let me be lazy. Ooh, Cauchy's mean value theorem. Interesting. I'm not proving L'Hopital's rule for you. Sorry if you wanted to see that. Ba-dum. Oh, come on. What's that?
You said over here, 1 to the infinity is an indeterminate form, but 1 meaning 0 to the infinity.
Something going to 1,
1 to the infinity would just be 1.
would it?
Huh?
Would it?
Oh, something going to 1. Right.
Because 1 plus n over x to the n goes to x over n. X over n goes to e to the x. This thing goes to 1,
Right.
whereas that goes to infinity, but that is not 1.
Is 0 to the infinity also another indeterminate form?
0 to the what?
0 to the infinity.
No, I think 0 to the infinity is just 0. As he sorry, I'm trying to find a fun example. But we also have, I mean, you know, we don't just talk about limits at, we're primarily interested in limits at infinity here, but because in this book we have not covered L'Hopital's rule at finite values before this point, also thrown into the mix are limits at like a finite value. For example, this one, he's got limit as x approaches pi over 2 from the left of tangent of 5x. I really should cover that in here because there are people who have not seen these things before, and it is an important part of the calculus sequence to talk about how L'Hopital's rule allows you to solve things like this. Honestly, though, if you can do it at infinity, you can do it at a finite value too. So I wouldn't be too mad at myself for leaving this out. There really are there are two major applications we have here of L'Hopital's rule. The one is the one I'm emphasizing the most right now, which is it allows us to calculate the limit of indeterminate sequences, right? Like if the sequence has a formula which is indeterminate as n goes to infinity, L'Hopital's rule gives us a powerful technique to calculate a bunch of them. The other thing, of course, which is of equal importance, is for limits as x goes to infinity, right? When we're not thinking about a discrete variable, we're thinking about a continuous variable, we're going to need to use that to formulate what are called improper integrals, which is what one of the things we'll be covering next week. Okay? So, anyway, let's do this example. What's the problem here? What type is this? What happens when you plug in pi over 2 into tangent? You get 0, right? Sine of pi over 2. Wait a minute. Infinity. It's worse. So, yeah, this is infinity over infinity. right? So yeah, the hospitals, yeah. So L'Hopital's rule. This time we do not have to extend n to be continuous here because we're not dealing with n, right? So this is 5 secant squared of 5x by the chain rule. And down here you got yourself just a secant of x, right? Oh, squared, thank you. Now, there's a right way and a wrong way to proceed. I'm pretty sure that I should not just apply L'Hopital's rule again, right? Seems like a bad idea. Let's see here. So if I rewrite this in terms of cosine, what do I have? Cosine squared, right? Over 5 cosine squared of 5x. Oh, the 5 should still be on the top. Yeah, that's fair enough. Yeah, duh. New math, sorry. Yes, thank you. And, okay, but now let's type 0 over 0, right? So this is a good example because it shows you, I write the L where I'm doing it, but not where I'm not, right? I don't write L here. I didn't use L'Hopital's rule to do this. I did algebra. So I don't write an L here. But I write an L here because I'm about to use L'Hopital's rule again.
Do you want us to show like 0 over 0?
Like this? Yeah, I would like that. I want you to explain what you're doing. So this is 10 cosine of x times minus sine of x divided by 10 cosine of 5x times minus the sine of 5x. You know, I think I picked absolutely the hardest possible homework problem in this section to do right now. Yeah. So we're still not done, right? Because it's what's going on here? We've still got 0 over 0. If you differentiate, apply L'Hopital's rule one more time though. I think this is the point where a light shines and it's not a train. Let's see here. So this is minus, so if I, product rule, 10 sine squared x minus 10 cosine squared x, right? And then downstairs I've got minus, cancel it. Oh yeah, thank you. Thank you, Nathan. That is helpful. Yeah, that less tens. Okay, so then sine squared minus cosine squared upstairs. Downstairs, what do I have? I've got, differentiating this gives me 5 minus 5 cosine squared 5x, right? Plus 5 sine squared 5x. Finally, I think this one is determinate because pi over 2 does what? It puts this to 0 and it puts that to 0, but this all together 1/5. And that is a nasty problem, but there it is. Yeah. Yeah.
When do we take the 5%?
The L thing, the 0 over 0.
Yeah.
When do we write that? Like up there?
When you're applying L'Hopital's rule. So I'm going from here to here. I have what?
Up there, you didn't write infinity over infinity.
Oh, I'm sorry. That's yeah. You're thank you. Yes, thank you. My bad. Take my points away. Oh no! I'm over time. You guys gotta stop me.
We're having fun.
No. You speak for yourself. This happened to me last semester too. I inadvertently started down this thing and I was like, is this ever done? Ah, stupid problem. Sorry, I will answer your homework questions from chapter 11 tomorrow if you got them. And I'll try to talk more about L'Hopital's rule. Thanks, guys.